Hello and welcome to our video solution to problem 3 from quiz 2. In this problem, we want to compute two definite integrals, but we're told in no uncertain terms, it's in italics and everything, that we want to compute it without using the fundamental theorem of calculus. Right, which means we are not going to be finding an antiderivative for the integrands of these functions, which frankly is a good thing because, for example, sine to the 23rd power, well, maybe I can do it, but boy, does that just seem exhausting. So instead, we want to use properties of these two functions, as well as our interpretation of an integral as just giving us the accumulation of the function. So let's start with sine to the 23rd power, and note that the bounds here go from -5 to 5. So I don't know exactly what the graph for sine to the 23rd power looks like, but I do know that the domain is symmetric, right, across the vertical axis. So it might behoove me to ask, is there some relationship between the values of this function, sine to the 23rd, on the right of the vertical axis and the left of the vertical axis? So let's say I had some value here. Let's call it, I don't know, how about a? And then I go to the other side. The opposite one would be -a. So is there some relationship between sine to the 23rd of a and sine to the 23rd of -a? Well, if I go to compute sine to the 23rd power of -a, I know, well, first thing, this is the same thing as sine of -a to the 23rd power. Now, the sine function does have a great property when it comes to putting negatives inside. It's what we call an odd function, which is that you can take this negative and pull it out of the sine function. So this becomes negative sine of a to the 23rd power. And now this negative, I could think of this as being a -1 times. So this is the same thing as -1 to the 23rd times sine to the 23rd of a. And if you have an odd number of negatives multiplied together, you still get a negative. So this is negative sine to the 23rd power of a. So this tells me that no matter what value I put in here for a, right, when I put the negative of it, it's going to give me the exact same value out except flipped. It'll give me a negative. So if my a gave me a sine to the 23rd that was positive, my -a would give me one that was negative. Right? So whatever this graph has to look like, and who knows what it's looking like, right? It's going to have to be symmetric. So here you can see it's coming down low. It's got to turn around and come back up. And what's going to happen? It's got to actually no, not come back up here. Where is it? After 0, it's actually going to have to be 0. Okay, so that's going to have to do something like that. And then it must turn around and go down. Why? Because this is up. So this is going to have to go down. Okay, and then when it gets back up to the A, it's going to have to be up here. We know that. Now, this is then going to have to turn around. Since this is a little bit positive when it gets to the 5, this is going to have to be a little bit negative when it gets to the 5. Okay, so every point, right, if I say this little peak, that's going to have to correspond to a little trough, right? And all of this stuff down here, that's going to cancel out with the stuff over here. And all of this stuff over here is going to have to cancel with all of the stuff down here. Okay, so everywhere that we have something going up, on the opposite side, we'll have something going down. Okay, the short way to express this is to say that sine to the 23rd power is an odd function. And we have a rule, which is that if you go from, say, some -a to a, and this f is an odd function, then all of the accumulation before you get to 0 is going to cancel with the accumulation after you get to 0. So this is going to equal 0. And so without computing any antiderivatives, we know the area or accumulation of this function is 0. All right, let's try the second one. So here, this looks very complicated, but let me give a name to this function. Let me just call it y. And if I square both sides, I'm going to get y squared equals 25 minus t squared. I did that because square roots are annoying. And now if I add t squared to both sides, I get t squared plus y squared equals 25, and 25 is 5 squared. And this is the equation of a circle. So this is a circle of radius, well, it's 5 squared here, so of radius 5. So I could actually draw a picture. And I just have to draw a circle of radius 5. Right? Except, note, if I go backward, at some point I'm going to have to take a square root. And when I take the square root, I should get plus or minus. But we don't have a plus or minus here. We just have the plus, which means I'm only looking at the top side, right? I'm only looking here at the top side of this circle, not the bottom side. Also, this tells me I'm only going from t equals -5. Okay, well, there's -5 to 5, because this is a circle of radius 5. And I only go from -5 to 0. So in fact, I'm only getting the stuff in this upper left quadrant, right? So this is just 1/4 of this circle. So this definite integral is just asking me how much does 1/4 of this circle accumulate? It's really just saying what's the area of 1/4 of this circle? Well, we know that a circle has area equal to pi times the square of its radius. So the radius here is 5, and so the square of the radius is 25. So we get pi times 25, but then we're only getting 1/4 of it, so we have to divide by 4. All right, and so our answer, right, 25 pi over 4. Again, no need to do an antiderivative, which in this case, we'd have to use like some sort of trig substitution, which we're not so happy about. This is way easier of an approach. All right, good luck. We'll see you next time.